Well, my name is Andy Schweitzer, and here's a short little procedural video on how to balance what I refer to as complex redox reactions. Now, the word complex or simple redox reactions are not something that you're going to find in a textbook. It's just my way of describing two different types of redox reactions. Now, a more complex redox reaction is one that could take place in an acidic environment or maybe even a basic environment. So these are reactions that require a certain type of aqueous medium in order for them to get to run. This first example is a reaction where I have dichromate, and in this case nitrite, but it's in an acidic solution. So in reality, this chemical is HNO2, which is nitrous acid. It's in a water solution, so water is also available. H plus ions and H2O are common components inside of this chemical reaction. Other things I might add that they may have the H in there already. Okay, they may have water in there already. Depending on how they set the reaction up for you to balance it, you should understand that those can be removed and you can start from scratch. Okay, which is what this one is. So the first step to balancing this literally is just like following directions. Step one is going to be to split into half reactions. All right. So I'll go ahead and I'll do that right here. And I have the half reactions are fairly easy to see. This is one half and this is the other half. So these two and these two are linked. So Cr2O7, 2 negative, goes to Cr plus 3, very common form of chromium. And then we have, at least for its most stable form, and then we have NO2 minus goes to NO3 minus. Before we get started, you should easily be able to label oxidation states to see who's actually being oxidized and who's being reduced. I could have done that beforehand, but again, that can be something you should be able to do. If a question just asks who is being oxidized, who's being reduced, list oxidation states out and answer the question based on charge differential. But that will also come out in the wash here. So first step is this, split into half reactions. Step two is going to be to balance non-hydrogen or oxygen atoms. Stretch this out a little bit here. There we go. And that would mean I would want to put I have two chromiums here, so I need to put 2 here, and nitrogens are balanced there. Okay. The next step is going to be, because we are in water and we're also in an acidic solution, I'm going to balance the oxygen with water. Okay, I'm going to move this a little bit. So, for example, here I have 7 oxygens here, so I'm going to add 7 waters to this side. And over here I have 3 and I have 2, so I'll add 1 water to this side. So literally you're just following directions. Got to be good at it though, and it has to be quick and effortless as you go through this. All right, because you're in an acidic solution, you would balance the hydrogens with H plus ions. Okay, this is the only step that would differ between acidic or basic steps, basic reactions. So here I have we have 2 hydrogens here, and so therefore we have to add plus 2 H plus ions this side, and I have 2 times 7 is 14, nothing else here, so I'll add 14 H plus ions to this side. Okay. Now my next step is going to be to simply charge balance each half with electrons. Okay, I'll show you how you do that. I like to write the charge right above the overall thing here. 14 positives and a negative 2 means this whole sign is a positive 12. This whole sign here is a positive 6. 2 times 3 is 6. There's no charge here. So to get these things to be equal, I'll have to add 6 electrons this side. And ding, 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 this is now a reduction reaction, and this is being reduced. Usually could have got that from the fact that the oxidation state's +6 down to a +3, getting electrons. This side, therefore, we expect electrons to be on this side. I have a -1 over here, and I have 2 positive, -1, so I have a +1 on this side. And therefore, I'll require to get them equal 2 electrons on this side. To get down +1 plus -2 is -1. So, all right. Next step is going to be right here, and 6 would be to balance E2 half reaction electrons. Okay, and that is very similar to all oxidation reduction reactions. We have this thing is consuming 6 electrons, so this one has to get rid of 6. Therefore, this whole thing is multiplied times 3, and we'll go 3. I like to lower my second number here a little bit, just so I can see the fact that I did this. Alright, so again, once those are all balanced, I like to rate them a little lower just so I can see what I changed. I'll grab my pencil here a second. At this point, it's simply a matter of adding everything up and combining and simplifying to get your overall balanced reaction. And I'll add that to our last step. Combine and simplify. Simplify means that if there's anything that's present on both sides, you can just simply cancel out what's on both sides. So at this point, the electrons will cancel. So that should always cancel. I combine all of these things on one side. 14 H pluses plus Cr2O7 minus 2 plus 3 H2Os. Now this is going to cancel with this guy down to 4. So I am going to eliminate that and say, okay, 3 NO2s goes to now all of this stuff. 2 Cr plus 3 plus 3 NO3 negatives plus 4 H2Os, and that's it. Everything else canceled. That's pretty much it, just following these directions. I would say you should be aware that there is, in fact, some spectator ions that aren't listed in the problem. Other than that, that's pretty much it. The only thing I do now is to practice a bunch and be able to do it swiftly and easily.